Ocean acidification is a problem affecting oceans throughout the world. Let's take a look at what ocean acidification is and why it's happening. Ocean acidification is when the ocean's pH is becoming more acidic. Normal ocean pH is about 8.2. Ocean acidification means that it's heading closer towards 7. But remember, even a small change in pH means major changes in acidity. The main source of ocean acidification is from CO2 emissions. CO2 emissions come from things such as gas from your car or the burning of fossil fuels. These CO2 emissions find their way into Earth's atmosphere. Once the CO2 has entered the atmosphere, it's absorbed by the world's oceans. Here, a chemical reaction happens and acid is formed. This acid is what lowers the ocean's pH. This is a confusing slide, but the main point is that once CO2 enters the ocean, a chemical reaction happens. After this chemical reaction, carbonic acid is formed. Carbonic acid is an acid, thus it lowers the pH. Here are two graphs to show you more about what I mean of when carbon dioxide is increasing, pH is decreasing. Here's an example from Mauna Loa, which is in Hawaii. As you can see, every year CO2 emissions have been increasing in the atmosphere. At the same time, pH has been decreasing in the oceans. Here's a graph for the projected pH and dissolved oxygen CO2 levels. Once again, as CO2 is increasing, pH in the world's oceans is decreasing. So why is ocean acidification a problem?
Marine pteropods, or sea butterflies, are found throughout the ocean and are a major food source for fish and other organisms. In laboratory experiments, this pteropod shell dissolved over the course of 45 days in seawater adjusted to an ocean chemistry projected for the year 2100.
Similar to what happened in the chalk lab.
What changes in the ocean might be putting pteropods at risk? The burning of fossil fuels has caused levels of carbon dioxide in the atmosphere to rise. This carbon dioxide, or CO2, doesn't just stay in the atmosphere. Roughly 30% of it is absorbed by the ocean. When CO2 reacts with water, it forms carbonic acid, which quickly releases a hydrogen ion, or H+. The more hydrogen ions, the lower the pH, or more acidic a solution is. As CO2 levels increase over time, seawater will progress towards the acidic end of the pH scale, a process called ocean acidification. We can make projections of this change in the ocean pH over time. It is expected that later this century, if CO2 emissions continue at the current rate, the average pH of the ocean will drop from 8.2 to 7.8. This relatively small decrease in pH may not seem significant, but it could impact many species of marine life. For pteropods, corals, and other species that depend on shells and exoskeletons, ocean acidification will lead to a decreased availability of dissolved calcium and carbonate, the chemical building blocks they use to make their shells and skeletons. If ocean chemistry changes as expected, shells with calcium carbonate mineral structures may begin to dissolve, depending on where they live in the ocean. How do we know that ocean acidification is happening? Scientists at NOAA and across the world have measured these chemical changes over the past 40 years during research cruises, taking hundreds of thousands of ocean water samples. Shown here are the results from cruises in 1991 and 2005, where the availability of the shell mineral was sampled. In both years, the highest concentration of available shell minerals were found in the surface waters as shown by the dark yellow colors. Deeper waters naturally have very low availability of these minerals. However, when we look at how these values have changed between 1991 and 2005, we see that the availability of the shell mineral decreased much more in the surface waters, as indicated by the blue colors. In other words, ocean acidification is impacting shallower areas much more than deep areas. Shallow waters are where the bulk of the ocean productivity occurs, including the most diverse and economically important species and habitats.
So all this really means is that the acidity is worst where most of the life actually lives.
And these changes aren't occurring in just certain parts of the ocean, they're occurring throughout the entire ocean. Today, repeated research cruises and permanent sampling stations continue to monitor changes in pH and availability of calcium carbonate minerals. As the ocean approaches a critical transition between shell building and shell dissolving, food webs in the world's oceans could be impacted. Phytoplankton and zooplankton, like pteropods, form the basis of most oceanic food chains. Coral reefs form the foundations of the most diverse marine habitats, and shellfish, such as oysters and crabs, and finfish, such as salmon, support economically important fisheries in many of the world's coastal communities. People depend on the viability of these species to ensure a healthy future of our own.
So if something down below the food chain, such as coral or those pteropods, are no longer able to live, it has ramifications for things living above the food chain, such as whales, fish, and then eventually humans.